Today in this section, we're looking at three topics. We're looking at talking a little bit about the domain and range of the sine and cosine functions. Right below that, we'll talk about even and odd functions, even and odd trig functions, and there's some patterns there we're looking at, and then finally a little bit of calculator work. So here we are, topic number one. Here's the unit circle with just the quadrant angles identified and those coordinate points. And what we're saying is if you rotate around, that's the input, right? So the sine function, every function has to have an input and an output to be a function, right? Every input gives exactly one output. So the sine function needs an input, and that input is the angle of rotation. Now you can rotate in the counterclockwise direction or clockwise, so positive and negatives are included. And as you know, you can rotate around again and again. So there's no upper limit to how many times you can rotate. So the domain is all of your inputs. What's the set of inputs? Right, here's interval notation. It's essentially all real numbers. You can plug in any angle you want, and we are guaranteed to get exactly one output. Now, sine, again, is always the ratio of two sides on your right triangle. It's always the opposite over hypotenuse, and the opposite side on your triangle is the height. So if you're thinking about a generic right triangle right here, this is my opposite side, which is describing the height, which that gives us the y coordinate. So the sine function is the opposite side over the hypotenuse, and the hypotenuse being the radius of 1 on the unit circle, right? So it's y divided by 1. That's why we say it's just equal to y. So the output then is the y coordinate. So we're saying, where is this y coordinate to be found? Well, at most it's a positive 1, and at least it's a negative 1. So that does have an upper and lower limit. Again, there's our interval notation. Similarly with cosine, cosine is the ratio of two sides. It's the adjacent over the hypotenuse. So this is your adjacent side of the triangle, which describes the horizontal distance. So that's the x coordinates of the point on that circle. Again, over the radius of 1, so you divide by 1. So we just say it's equal to x. So again, the input is any angle of rotation. That could be all real numbers. But the output is going to be bound between -1 and +1. Those are your x coordinates. So that's the output. So even though it looks like the same numbers, these are representing y coordinates, these are representing the x coordinates. What that means for us is that then we can find the sine and the cosine of any angle, even really, really big angles or really, really small angles. We will always be able to get an output. And that's what we're looking at here. This is a general concept of this spiraling around, the angle's getting bigger and bigger. So as you go around, you're starting off with an angle of pi over 4, then pi over 2, and then 3/4 pi, and 1 pi, and go all the way around to return to where you started with, and you can keep on spiraling. So now this is that angle of pi over 4 plus a full rotation of 2 pi. If you go around again, you would add another 2 pi, and so on. So the dot, dot, dot means you can keep adding another rotation. So we were talking about these when we were talking about coterminal angles, right? When we're finding coterminal angles, we're identifying another angle that terminates at the same spot. So the trick here is we'll take that really, really big angle, and we will subtract 2 pi as many times as it takes until we get back to the angle we're more familiar with in our unit circle. Or if it's a really small angle, we'll add 2 pi and add 2 pi until it returns to an angle that we're more familiar with. So that's what you're looking at here in examples 8 and 9. Here we have the sine of -8/3 pi. We don't really know where that is. I mean, we could figure it out if we drew the unit circle and sort of counted our way around, but the concept here is let's evaluate its coterminal angle instead. So this is a really negative angle, so I'm going to add a revolution. Let's add 2 pi, and that means we need to match that common denominator of 3. So what we're saying is this is equivalent to finding the y coordinate at this angle. So -8/3 pi plus 6/3 pi, that's -2/3 pi. All right, so now that's within one rotation, clockwise rotation of the unit circle. Do you recognize where we are now? You could add another 2 pi and turn it into a positive angle if you wanted, but that's the concept. These are coterminal angles, so if we evaluate the y-coordinate here, it'll be the same as evaluating the y-coordinate of the original problem. So just as a quick reference, in case you're not sure where we are on the unit circle, we are right here. That is our angle of -2/3 pi. So there's your circle. There's -1/3 pi. There's -2/3 pi. So we want to know what is the y-coordinate at that point. So that gives us a result of negative root 3 over 2. Here's example number 9, cosine of 9/4 pi. So that's a really big angle. Let's evaluate that, finding the x-coordinate at a coterminal angle. So let's subtract 2 pi to make that angle a little bit smaller. Sorry, we want 4 over 4 here. So this is equivalent of evaluating the cosine with an input of, so 9/4 pi minus 8/4 pi is 1/4 pi. You recognize where that is? That's in quadrant 1. Cosine is the x-coordinate at that angle, so that's root 2 over 2. So that's topic number 1. Topic number 2 now has to do with patterns that we're going to be identifying here soon with even and odd functions. We talked about this in our function unit, what makes even, what makes odd functions, and we're going to draw some pictures here to help explain this because this can be kind of tricky stuff and we need to draw the picture to help make some sense of it. So I'm going to use the margin space here to be drawing little sketches of things. You want to take a look at the difference here between the if part and the then part. We'll do our examples here first, and then we'll come back and we'll add some additional information here with the function notation and try to explain what that means once we've seen the pattern. All right, so the if is what's given. They're giving you something, and then once you have that given information identified, then we can answer the questions here. So what we have is sine. Sine is the y-coordinate. So as I look at that, we're going to evaluate this function, and I'm going to be working with the y-coordinate. And you can see it, there it is, there's the y-coordinate. But notice what matters here is whether it's positive or negative. This is a positive y-coordinate. That's what matters here. We also have identified the direction of the rotation, right? That's a positive t, as opposed to this, which is a negative t. So that means we're going to rotate in that counterclockwise direction. So here's my sketch. We're kind of abstracting this because we don't have an exact angle to place on here. What we're doing is we're going to sketch this so that we have our initial side, and then we have to figure out where does the terminal side go so that my y-coordinate is positive while rotating in that counterclockwise direction. We'll go through as many quadrants as it takes, but we'll use the first quadrant that we get to that meets this criteria. So here in quadrant 1, we can find a y-coordinate that is positive. So again, I'm abstracting this. I don't really know where this angle t is. We don't know if it's big or small. And we're not solving for it either. We're not finding it. We're just saying it's a direction of rotation in the counterclockwise direction. That means this point on the unit circle is some x-coordinate, and the y-coordinate is positive 1/4. That's the given information. Now what they're asking us to do then is find sine. That's the y-coordinate again. But notice what happens. The input is changing. We're changing the direction on the input. Instead of a positive input, we now have the opposite input, the negative input. So that means we have to rotate in the clockwise direction. So think of like copying and pasting. You're going to copy the size angle that you already drew down here, but rotating in the clockwise direction means that my terminal side is going to be roughly there. So this is my negative t. That's my input. We want to know what is the output. The output is the y-coordinate. So we're asking ourselves, what is the y-coordinate now that we're in a different quadrant? So there's the x-coordinate we don't know, and the y-coordinate has to be negative because we're in quadrant 4. So this is the idea. We figure out what quadrant we start in with the given information, and then we figure out what quadrant do we end up with when we change the direction of our rotation. And again, we're looking at the y-coordinate because that's what sine is all about. Cosecant is the reciprocal of that sine. So we're just taking that y-coordinate and flipping it upside down. All right, let's take a look at another example, and then we'll see if we can find some patterns here. So here in number 11, we are given that sine of negative t is positive 2/3. All right, so again, notice what we're identifying. We're identifying that we're working with sine, so we are working with a y-coordinate only. And again, notice we have a positive y-coordinate, positive 2/3. And notice the direction of rotation, that's negative, so we want a clockwise rotation. So here's a sketch. All right, so here's my initial side. We have to rotate in this direction, the clockwise direction, because of the negative angle. And we have to keep rotating until we end up with a y-coordinate that is positive. We want a positive 2/3. If I rotate into quadrant 4, well, that's a negative y-coordinate. If I rotate into quadrant 3, my y-coordinate is still negative. So keep rotating until we get to the next quadrant, quadrant 2, where my y-coordinate will be positive. That's my angle that we're working with. That's the given angle. And so here the x-coordinate is unknown, and the y-coordinate is a positive 2/3. So now what we're doing is we're going to change the direction of the rotation. Instead of rotating clockwise, now we're going to rotate counterclockwise. We want to go this way. So it's the same size angle. So we went through half of a circle's rotation plus a little extra. So do the same thing, but now in the counterclockwise direction. So here's my initial side. We want to go through half of a circle's rotation and then a little bit extra. So something like this, for example. So this is located at x comma negative 2/3 because now we're in quadrant 3, the y-coordinate becomes negative. So that answer is negative 2/3. And we want the reciprocal of sine. Cosecant is the reciprocal of sine, so we have negative 3/2. So the pattern that we're looking at here is when I change the direction of the rotation, the y-coordinate will end up at a different quadrant and it changes its sign. So if we start with positive, we end up with negative, but if we had started with negative, it would end up as positive. So let's take it back to the pattern. Which of these patterns are we observing here? There's two possibilities. This is the notation that says you have your function and you are inputting the opposite rotation, right? So negative theta. What kind of answer are we getting? This is saying you get the original function's answer. Is that what we have here? Do we have the original function's answer? No. It's the same numbers, but the signs are changing. So it's not this one. An odd function occurs when you take your function, you plug in a negative input, and the answer is, it's really tiny, but there's a minus sign right there. It's the opposite sign of that function's original answer. That's the pattern that we're seeing here. It's the same numbers, but the sign is changing. So we say that sine and its reciprocal, cosecant, are odd functions. We see this behavior. So anytime you change the sign on the input, you also change the sign on the output for the sine function. Now that must mean that cosine is even. So we'll go ahead and fill that in. Even for both cosine and its reciprocal, secant. Right, and we'll see those examples on the next page. So this time when we change the sign on the input for cosine, the answer, we will not see a change. So let's see how that works. Okay, so top of the next page, here's examples 12 and 13. And then also we have some additional notation to describe as well. Just prepping my circle here. All right, so here then is my given information. So this time the cosine is describing the x-coordinates. And there it is. Notice the x-coordinate is negative. And we're determining which way we rotate. It's a negative t, so we go clockwise. So here's the initial side. What that means for us is we have to keep rotating until our x-coordinate is negative. If I'm rotating into quadrant 4, my x-coordinate is positive. So keep rotating until we get to quadrant 3. Somewhere in quadrant 3, our x-coordinate is that negative number. So negative 2/5, and the y-coordinate we don't know. So just leave it as a placeholder there. That's the given angle. So now the question is, we're still evaluating cosine, so we still want the x-coordinate, but we're changing the sign on the input. Instead of negative, now it's positive. So we're rotating in the counterclockwise direction. We want to go through a full quadrant plus a little extra. So here we are rotating through a full quadrant plus a little extra. There's the terminal side. The question is, what is the x-coordinate now that we're in a different quadrant? Well, we're in quadrant 2, and therefore the x-coordinate is still negative. Look at that. The output, the x-coordinate, is still the same. So negative 2/5 is the answer. So let's take the reciprocal. Secant is the reciprocal. Here they're using the original angle, so flip that fraction upside down, negative 5/2. Now what you're looking at here is different. We haven't seen this yet. What is pi plus t? What is that angle? All right, so here are some additional notes for some of these extra angles that we're going to be working with. So if you have pi plus t, or t plus pi, either way, what that means for us is that we need to add half of a revolution to the given angle. The given angle t in this case. In other words, we're making our angle even bigger. We're taking the original sized angle and then we're adding pi. So think of that in degrees. That's like adding 180 degrees, right? That'd be half of a circle's rotation. So we're adding half of a revolution to that given angle t. So going back to our sketch, here is my given angle in green, right? Because we're using the positive t here, not the negative t. So we're using this positive t, so that's what I did in green. And then from here, we want to add on an extra 180 degrees, or an extra pi radians, if you will. So here we're adding pi. And so now this is the terminal side. So it looks like one long straight line, and that's what happens, right? When you add half of a revolution, you end up on the opposite side of the circle. So the question is, what is my x-coordinate now? Well, now we're in quadrant 4, so now that's a positive 2/5. So that answer is a positive 2/5. Let's set up problem 13, then we'll come back to this little note section. We'll add these details in here in just a moment. All right, so again, here's my sketch. Now for this one, we're going to end up needing to draw 2 of these circles, so I'll go ahead and prep both of those. All right, starting off with our given information, we have cosine, so again, that's the x-coordinate, t, that tells us the direction of the rotation, and the x-coordinate is positive, 4/9. So we can rotate right into quadrant 1. There's my angle of t. This is an x-coordinate of 4/9 with some unknown y-coordinate. Okay, so that's the given information. So what you see here is quite different. They're asking us for a completely different angle. They're not even going back to the pattern we've been observing so far. If they did, we know what would happen because we've seen the pattern. This is something new. So what does pi minus t mean? All right, so pi minus t, this is in our note section, means this is a new angle. This is the angle is a supplement to the original angle t. This is a supplementary pair of angles. The original angle is t. The supplement is something that you would add up with the original angle so that they total up to pi radians. So on our sketch, we know where pi is. Here it is on the far right-hand side. So we want 2 angles that add up to pi. So if the original angle is t, then that means this is its supplement. So I'm putting that here in green. That angle right there is a sized angle of pi minus the original angle of t. So that's the notation that we're seeing. Pi minus t is the supplementary pair. We have a problem, however. This angle is not in standard position. We have to redraw it. So that's what this second circle here is for. So here's a little note of what I'm doing. I'm going to redraw the supplement. That supplement is the angle of pi minus t. All right, so we're going to redraw that. We have to draw it in standard position, which means one of these sides has to be placed here on the horizontal x-axis. So we're, again, sort of copying and pasting it here. Same size angle, so it's like a quadrant plus a little extra. We're going to rotate through quadrant 1 plus a little extra. There it is. And the question is, what is the x-coordinate now? Well, now we're in quadrant 2, which means that this x-coordinate is negative 4/9. And that's our answer, negative 4/9. All right, here's the last one, 2 pi plus t. So 2 pi plus t, it's very similar to the first one. If it was 1 pi plus t, that added half of a revolution, so 2 pi means go all the way around. So 2 pi plus t means to add a full rotation to the given angle that they provide us, t in this case. All right. So what we need to do now is find the original angle and make it bigger, 2 pi bigger. So here is my original angle of positive t. There it is in red. And so we're going to add on to that a full rotation, and of course we end up back where we started with. That's a coterminal angle. What is the x-coordinate? It's still that positive 4/9. Now eventually, I'm hoping that you can do some of these problems in your head. If you can picture in your mind's eye where the angle is originally drawn, and then how to replace it with the change of input. But if you can't quite see that, that's okay. Just draw the picture like what we've done here. Identify your original, your given information, and then how it would be relocated with the change in direction. All right, so that's topic 2. The third topic here is evaluating some of these problems on our calculator, and there's a couple of things to keep in mind. Notice, again, these are your inputs, right? So you're plugging that into the calculator, of course. But what exactly are we inputting? Doesn't matter if it's sine or cosine or the reciprocals or tangent or cotangent, right? What we're putting in is an angle of rotation. So we need to know, is that in degrees or is that in radians? There's no degree symbol here, so that's obviously radians. So if you're plugging in a radian, then you need to use radian mode. If they told you to plug in a measurement in degrees, then you would use degree mode. So if you have a scientific calculator, you're going to find that change here where it says DRG. That button is right next to the top left corner. And selecting that, you can use your arrow keys to toggle back and forth between degrees, radians, and even gradients, but we're using radians in that case, right? If you have a graphing calculator, you want to hit the mode button, and in the mode button, you'll toggle between degrees and radians as well. However, the second issue is we have a sine button, a cosine, and a tangent button. There is no such thing as a cosecant button. There is no such thing as a cotangent button, right? These don't exist on the calculator, and that's because they know, we know, these are reciprocals of certain functions, right? So cosecant is the reciprocal of sine. So it's the same input, it's the same angle measure of 1.3 radians, but to get this value, this is the reciprocal of that sine of that angle. So we're going to enter in 1 divided by the sine of 1.3, and that's the trick. We'll go to 3 decimal places. Cotangent then is the reciprocal of tangent. So what is 1 divided by tangent of 1 radian? 0.642. Right, and then lastly, the secant here, that's the reciprocal of cosine. Cosine of 22.8 radians. That's a 1.449. And again, it can be negative, right? Because we said that our outputs are going to be somewhere between negative and positive. But notice we said the upper and lower limits were 1s, -1 and +1. But that's for sine and cosine. If you reciprocate those decimal values, you can get decimal values that are outside the range of -1 and +1. That's why you see these results as being outside of that normal range of your sine and cosine range.